Record. All right. So the time is 3:04. Alrighty. Let me do the share. Phone. And the questions. Very nice. Yeah. Okay. So it's chapter 24, number 39. It's like a good one here. And then I got the questions. All right. So 30, what does 39 say? 39 says a long straight wire is surrounded by a hollow metal cylinder whose axis corresponds with that of the wire. The wire has a charge per unit length of lambda. The cylinder has a net charge per unit length of 2 lambda. From this information and from Gauss's law, use the charge per unit length on the find the charge per unit length on the inner and outer surface of the cylinder, and B, the electric field outside of the cylinder, a distance R. Okay, so let me come back here and try to draw a picture. We have this long straight wire. And so maybe I'll draw it in a vertical fashion. So there's a long straight wire. It's also surrounded by a hollow metal cylinder. So I'll try to draw a metal cylinder that goes around. Like that. So wish I could erase right there. All right. So here I have. So a long straight wire surrounded by a hollow metal cylinder whose axis corresponds to that of the wire. The wire has a charge per unit length. So I'm going to put a little lambda right here on the wire. And the cylinder has 2 lambda. Now, that's interesting. So it's not an opposite charge. It's the same charge. Okay. From this information, use Gauss's law to find the charge per unit length on the. Okay, now maybe I'll do B first. Find the electric. Well, yeah, B might be a little more straightforward. They both involve Gauss's law. The electric field outside of the cylinder. So outside of the cylinder would be a Gaussian surface that would be something like this. And maybe I'll actually just do a finite length L to the Gaussian surface. But the other ones, the fact that they say is long is going to be an important step, as I think you heard in the other sessions, as well as the one you were asking about, number 47. So when you see the video on that, I think you'll like that. I spent a long time at the beginning talk about the lines of symmetry. But I also talked about that in 55 and 57 and 29. And so I think those were all the ones that were asked today. So I'm going to end up doing the same thing here, where I'll start off with Gauss's law. And the first thing is a discussion about the lines of symmetry. And in order to justify the lines of symmetry, we have to have a long, they say that. And our argument, really, they have to be infinitely. But obviously, in reality, you can't have infinitely long. But since we know the effects of the electric field taper off with distance, if we just have something long, we can pretty much justify, well, it's almost the same as if it was infinite, because the pieces that are further out play such a small role. It's the close ones. So this long straight wire surrounded by a metal hull cylinder is going to be this big step, because I'm going to take this dot product, and so EDA cosine theta as the first step. And then when I do that, of course, my drawing doesn't really have a wire that looks very long, but maybe over here on the side, I'll put a real long wire. Well, without the cylinder, and then just draw a horizontal line, or a line perpendicular to the wire. Because is that a line of symmetry? Now, if the wire had a finite length and you drew it right in the center and flipped it, you would say, well, yes. But if you drew it to closer to the top or closer to the bottom and flipped it, you would say, well, once you flip it, the smaller side is now on the top and the longer side is now at the bottom. And the small side and the short side switch roles. And so that's true for a finite size wire. So my argument here is going to be that this is only going to work if our wire is either infinite or so long that all the places we're interested in the field. And so you might say near the middle of the wire. When you flip it, you have just as much charge to the top and to the bottom. So this is a less than perfect argument of symmetry. But again, I'm sure it's why the author says a long. He starts off with long, because now I can draw a bunch of lines of symmetry. All of these are lines of symmetry, as long as I'm not too close to the edge of the wire. And so our argument before, and I'll say it again, that the lines of symmetry are important because of our argument that the lines of symmetry must be the directions of the electric field. And maybe it's worth saying one more time. I'll even turn the paper kind of on its side this way. Here is our argument of why they have to be lines of symmetry. If you have an electric field that was not along the line of symmetry, so I'll draw kind of this orange one off a little bit. And you imagine this wire being flipped. And so all the charges that are on this side of the wire and all the charges on this side of the wire change places. The left goes to the right and the right goes to the left. Okay, so you'll flip it. But the thing is, if it's a line of symmetry, you'll get the same pattern of charge, what I call the same distribution of charge. Okay, but by flipping it, you would then change the field here. And that's where you would have to say, well, that can't happen. You can't end up flipping it and result in the same distribution of charge, but yet have a different direction to the field. If you end up with the same distribution of charge once you flip it, you got to end up with the same direction as the field. And so that can only be done if the electric field is along that direction of symmetry, that line of symmetry. Because that way, if it is along the line of symmetry, when you flip it, it still points in the same direction. And the charge distribution still looks the same. And that makes sense. It's when you flip it and you end up with the same charge distribution, yet you end up with a different direction to the electric field, which makes no sense. The electric field is created by the charge distribution. So the same charge distribution after you flip should end up resulting in the same direction of the electric field. So lines of symmetry play that important role. And so you'll see, but like I said, when you go back and look at 47, I spent a long time on this one, but I did it again because not everybody's going to have time to see all of them. So I did it in 55, I did it in, I think in 29, I did it in 24, and I do it now here in 39 here. So lines of symmetry here for Gauss's law is a big part of Gauss's law, because that gives us the ability to figure out where or what direction the electric field is. And the reason that's important is this first step in the dot product right here says, give me the angle theta. And in order to get the angle theta, which comes from this dot product, you have to know the direction of the electric field and the normal. And so now I just argue, I know the direction of the electric field. Now, of course, I drew just left, right. I tried to do more of a 3-dimension. If I did a top-down view, so here's the wire with lambda, here's the cylinder around it, charge density of 2 lambda, and you were saying I was drawing lines of symmetry kind of this this way, but I would be better from the top to say lines of symmetry would exist in a radial direction. And so the electric field would be, and I'm going to use a phrase I did before for the spheres. The spheres, I meant radially outward from the point. These, I mean radially outward from the z-axis, from a cylinder. I take a piece of paper here and make a cylinder. Look from the top down. I'm saying the electric field looks like this, 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 and so it's radially outward around a cylinder. So back here in my drawing, the electric field would be pointing radially outward as we go around the cylinder. So go out this way. And it's perpendicular to the z-axis. So it would be cylinder go out this way as well as up towards the screen over here. So that's the first and important part here of this, is I have an idea of the direction of the electric field. And not surprisingly, because this is how we need to set up our Gaussian surfaces, if this green here is that Gaussian surface, so maybe this computer pin is the wire, and this piece of paper is the Gaussian surface. So if I do something like that, then the normal vector or this cylinder is also what I'd call radially outward in a cylindrical case. That is perpendicular to the z-axis as we go around the z-axis. Give me something to point with. That will fit on the screen monitor. I'll use this nail here. So that would be the normal vector, and that'd be the normal vector, and that'd be the normal vector, and then be over here be the normal vector, and the normal vector, and the normal vector, and the normal vector. So this arrowhead, if the screw is an arrowhead, is representing my normal vector. Okay. But it's also the same argument I did for the electric field. And that's just a long way of saying that this number right here then would be 0 degrees. That I just argued from the physics that these two, or from the physics, this one, the direction of this one, and I know that one from the geometry, but these two together, then I know there are two directions and the angle is 0. And of course, in the second half is to argue that E is a constant on the Gaussian surface. And that argument would go, again, something like this. If this is this configuration with all these charges as my cylinder, if I were to move over a little bit, on this picture here, maybe on the Gaussian surface right there, and maybe compare it to some other place, like right here on the Gaussian surface, so here versus here, the charge distribution looks pretty much the same. You look back here and you see all this charge. You stand here and look back, you see all the same charge distribution. Now, again, that same charge distribution is what makes that electric field. So you expect it to be a constant on that Gaussian surface, which is our justification of pulling it out. So it's, again, those two big steps that we need to do first. And those are easy to justify with the appropriate Gaussian surface. So the appropriate Gaussian surface is a big deal. It gets rid of this cosine of the angle. And I guess it doesn't always have to be zero. The easier cases are zero. That's what we've been dealing with all day today. But usually the best Gaussian surface makes that a zero. And of course, definitely the best Gaussian surface makes this a constant on that surface, so you can pull it in front. So now you're doing an integral that is clearly just area. And you don't have to worry about trying to integrate the electric field times the area when you don't even know what the electric field is. I mean, that's this whole problem of B. B says the electric field outside of the cylinder a distance r. So now I can get the area. Now, need to be careful. There's a bunch of areas in this problem. The wire in the middle has a surface area. This cylinder around it has an inner surface and an outer surface. So those are areas. And those are what I call physical areas. So we got those. But in addition to that, there is this Gaussian surface, which I call a mathematical surface. And the question would be then, which area am I talking about in all this? And it is the Gaussian surface. It is the mathematical surface. That's what this says. This says the flux in or because of this Gaussian surface. Okay. Messed up my screen here. Well, I'll leave it for that for a moment. Go come back a little bit later. But this then is that area of the Gaussian surface. And so maybe again, taking that piece of paper and rolling it up, if you will. So I have something to look at in 3 dimensions of my Gaussian surface. This Gaussian surface, this represents this green surface here. Then I would say, all right, I have, and I can unroll it and then say, well, what's this surface area? Well, it's this length. Well, that's the circumference of it times its length, which I called L. And the circumference would be 2 pi r. So this area would be 2 pi r times its length. Now, the charge enclosed is crucial to where I'm drawing my Gaussian surface, because if I were to draw my Gaussian surface between the wire and the cylinder, I would only enclose the wire. But I believe part B said they wanted the electric field outside of the cylinder. So I drew a Gaussian surface that incorporated not only the wire, which has a charge density of lambda per length, but also the cylinder, which has 2 lambda. And this is why I needed to go back. Let me change my screen back to the question. 39, just to kind of double check. B says the electric field outside of the cylinder. So they have a wire and then a hollow metal cylinder. So we only have to do it on the outside. Some of these other problems, we have to do it all over the place. And I think we actually need to do it for part A anyway. So, but I'm just going to do what they said on the outside. So when they say, what is the charge inside? If I did 1 meter of length, I would have lambda times 1 meter plus 2 lambda times 1 meter. So I guess it would look like this: lambda times length plus 2 lambda times length. That's how much would be enclosed in a Gaussian surface that had length L. So lambda times L is the amount of charge that is on the wire, and 2 lambda times L is the amount of charge on the cylinder. So that's the total charge inside and divided by epsilon naught. Now these are like terms, so this can simplify to 3 lambda L. And then, of course, notice the L shows up on both sides. So I would get, and I'll bring the 2 pi together with the epsilon naught. And then that would leave me with a 3 lambda and an r. So this should be part B. What is the electric field all the way out? And maybe I should just say, now that we've done a lot of problems for this chapter, this hopefully is not a surprise, because we've seen this for spheres as well as cylinders, that once you get on the outside of the sphere, the electric field comes out to be the same as if it was just a point. And the same thing about a cylinder. Once you get outside of the cylinder, you get the same field as from just a line of charge. So this whole thing could be thought of as just one line of charge with a charge density of 3 lambda. And so that is the equation that was worked out for a line of charge. This right here was the charge density. Just we have 3 lambda instead of just a lambda, as was worked out in the example. Now, before I go back to B, I probably should just check that I'm not off step yet. Let's see, they've got the 3 lambda, 2 pi epsilon non r for part B. Oh, they do go on to do a little better and say radially. And so I'll do the same thing. But again, like I said earlier, got to be careful with the word radially outward. This is radially outward in cylindrical coordinates, not radial outward as spherical coordinates. So that's important to note. Well, again, let me call this page 1, like a lot of the other ones, because these can get pretty long. And let me go then to part A. Now that I did it out of order, I did B first. And I did that only because part B, I think, is harder. It's a judgment call here. But it says the charge per unit length on the inner and the outer surfaces. Let me come back and draw a top-down view of the wire and the cylinder. So looking down the top, you would see kind of a small circle for the wire. And then the cylinder would have an inner radius and an outer radius. Maybe just to remind myself that these are the physical solid pieces. I'll color them in a little bit. Oh, and maybe I better put page 2 here. I bet. Nah, maybe not. I'd say maybe we'll end up with a page 3, but maybe not. I've already done B. But now I'm going to make a move and do a Gaussian surface. Oh, bummer, I've been switching colors here. But anyways, let me just do a Gaussian surface in red this time. Stands out from the physical. But again, the key to all these problems, which you get from experience, is to recognize that a Gaussian surface, the correct Gaussian surface, the best Gaussian surface, really makes these work out. Otherwise, it's just too complicated and too hard. And you'll have to do these by other techniques if you can't use the Gaussian surface here. But I picked this one that's actually in the hollow metal. That's the key cylinder. Because if you come back to what we did in B, starting with Gauss's law, arguing that we have these lines of symmetry, so the electric field has to be radially outward, and the normal is also radially outward, so the angle is 0 degrees. that we would always have the same distribution along the Gaussian surface, so the electric field would be the same. We would get to this point just like we did in step B, although step B, the Gaussian surface was outside of both of them. I would say these are still the same. In fact, even this step is the same. So I'm going to start A there and say, okay, so this would be E times the area. So that's 2 pi RL equals charge inside over epsilon naught. So we're this step, where I took that and set it equal to that. Now, in B, I was able to figure out how much was inside of the Gaussian surface because I was told the wire was a lambda and I was told this was on the cylinder. Of course, I don't know really how much is on the inner surface and how much is in the outer surface. So this step, I'm going to run into trouble because I could do the wire. I could say lambda L plus, but I run into troubles trying to say how much is here because that would only be the stuff on the inner surface and not the outer surface. And I guess I don't know that. But that's perfect what I want. I'll just put a question mark there because that is this question of A. It says, what is the charge density on the inner surface? And I'll say it again. And in part B, I just put here, 2 lambda times L for the charge on the cylinder because they told me that was the charge density. And I know since it's a metal, some is on the inner surface and some is on the outer surface. But how it distributes itself depends on a lot of factors. And so I don't know what's just on the inner. So that's why in A here, I have to just put a question mark and say, I don't know. The great thing, though, is what I also know about metals is over here on the left-hand side of the equation, the electric field is 0 inside the metal. And so I'm going to take that to my advantage and then put a 0 for this left-hand side. And so that means lambda L plus whatever the charge density is. So let me just put lambda inside times L.
Electric fields are always 0 on metals?
Inside a metal. Yeah, yes.
Inside a metal, okay.
Inside a metal. And the argument goes like this, that if it was not, that means there would be a force on those charges that are in the metal. And the metal's a conductor, and that would move the charges. And they would move and move and move, and they would continue to move until there is no more force, which means there's no more field. So that's a strong argument in here. Now, I guess for a little more clarity, I guess I would say there would be an electric field for a short amount of time as the charges are redistributing themselves. But once they redistribute themselves and reach static equilibrium, there's no more electric field.
Oh, that's true for any closed surface, right?
Now, that's true for any metal.
Oh, okay.
Here, closed surface, I'm starting to think of the mathematical surface of Gaussian surface. This is, I'm talking about a real metal here, a real surface. So two things to keep in mind about metals. One is that after the first millionth of a second, there will not be an electric field in the metal itself. And once those charges spread out and distribute themselves, those charges will only be on surfaces of a metal. So in this problem here, that's why I was saying there's probably some charge on the inner surface and some charge on the outer surface. And I've enclosed only the inner surface. Whereas in part B, I enclosed both the inner and outer surface. And I know that total to be 2 lambda. I just don't know how it's, divided itself. Right. So yes, right here, I'm taking advantage on the left-hand side. I know the electric field is 0. So then I would have the lambda from the wire times L plus the lambda on the inside surface times L. And that's what I want to find. And of course, if I move this over to here, I get 0. If I factor out an L and move it over, I get 0. And so that tells me that lambda of the inside must equal negative lambda. And so the lambda is the charge density of the wire. So if I were to draw a picture of what I know so far, and they don't tell me if lambda is a positive number, but for discussion reasons, I'm going to take lambda as a positive number. So there's the positive on the wire. And then if this is the inner surface, here's the outer surface, then there must be the same charge per length there. And it must be negative. And of course, that kind of hopefully makes sense now, because in order for the electric field to stop, see, the electric field is generated from the wire and goes radially outward. But in order to stop, because we know the electric field does have to terminate, it has to stop because it's not supposed to be an electric field inside the metal. It's got to hit a negative charge. And so electric fields terminate on negative. They start on positive and terminates on negative. So not a surprise then that it's negative. And also not a surprise that it's the same number, because whatever gets started has to get terminated. We don't want to terminate extras or fewers. If we terminated a fewer than were started, then some would actually get in the metal. And so you almost could have guessed this at the beginning, saying, okay, the inner surface has to terminate whatever started. And so that's not a surprise. It's a little better to see it in the math, but it's not a conceptual shocker to see that, wow, oh yeah, it terminates itself. That makes sense. Okay, so now that we have the inside, remember this, that the 2 lambda is the charge density of the whole metal cylinder. And so that would be lambda of the inside plus the lambda of the outside. Maybe I'll say it again. Remember, this is a metal, and we know the charges are only on the surface. So in order to get the total charge per length, we have to add the inside surface and the outside surface. And of course, we just found the inside piece. So I will put a minus lambda here. Find the lambda, the outside, which is perfect because now this is 3. And that, of course, again, makes sense. Notice it's positive. Coming back to this picture, then I would say, well, then there's a bunch of positives around it. And the 3 makes sense because, again, the net has to be 2, and we've got 1 lambda on the inside. And then, of course, that would reinitiate the electric field on the other side of this cylinder. And it would reinitiate it with a strength of charge coming from a 3 lambda, which matches what we did in part B, where we found the electric field as it is equivalent from a wire of 3 lambda. So that's why it's equivalent of 3 lambda. There's 3 lambda on the outside, which I think we kind of argued that it came from some in the middle and some in the wire and some on the cylinder. And although it's technically true, the stuff in the wire was terminated by the inside piece. So to get the 3 lambda, there must be the 3 lambda on the outside piece. So there's the charge on the outside, the charge density. That might be the end of the question. The charge per unit length on the inner and outer surface. Yeah, good. And I suppose I should just double check. That one seemed straightforward enough. Minus lambda and 3 lambda. Nice. Another good one, and another good long one. All right, let me switch my big screen back over to the chats and say, anybody throw in? I see James came in a little bit. I don't know if you had more for me on capacitors, James, or kind of listening in.
Yeah, I'm just I got my home whiteboards there, and I don't have any questions at the moment.
Okay, all right.
Just I said there's someone else out there struggling.
Let's see. I remember it must have been you, unless somebody else is using a whiteboard, but somebody sent me a question, which was a photo off the little mini whiteboard. And they said, hey, what's wrong with this? And I answered it. Was that you?
That was the triangles, yeah.
Triangle.
He said mine wasn't in the right plane.
Oh, yeah,
It's a
right.
cube, and I was trying to connect the corner to the center.
Yeah, that's right. Yeah, that was good. And that was a challenging one, too, because I followed it and I go, usually when I get a question like that, I can scan it really quick and I go, oh, yeah, I see where the student's going wrong. But on that one, I was like, huh. I go, that looks really good. And I go, what's going on here? And it took me a couple of minutes. I had to, play with my hands. I had to see it in 3 dimensions before I realized, oh yeah, the triangle he's drawn isn't in the same plane. So I was like, oh, okay. And actually, that gave me a chance to write on my screen. I said, oh yeah, I can check out my new pin here, and so I did my screen draw, and I go, okay. So
hey, perfect. This stuff is this is pretty hard. It's definitely harder for me than 121.
Oh yeah. And I hope I didn't scare anybody at the first email I sent out, but I said, hey, start early because we hit some hard stuff.
Yeah, you think like, it's pretty subjective and it's going to vary, but like in the email, you said these first 4 chapters are some of the hardest of the course.
Yeah, I'd say 3 because I don't know if the capacitor is quite as hard as the first 3.
I find capacitance to be the hardest for me by far.
Okay.
Out of the, but I think it's like the higher level of abstraction. Like my friend in high school, he read this book on like set theory or something.
Okay, yeah.
Which I would never touch. Like I'm just like I don't care.
Yeah.
But if you can give me like the particles, I can kind of like feel, you know what I mean? Like the inverse square law, like that's abstract.
Yeah.
But it's still pretty physical,
Oh yeah.
But you
and I would say, I would say you're right that this is tough. But I wouldn't say it's as tough because it's so much abstract. Although I would say it's a little abstract. I would say the couple of big reasons why I think this is so much harder than 121. One of them is what you're touching on. We're drawing these Gaussian surfaces, and that's kind of abstract. However, it's physical in the sense that it's 3-dimensional. But that's why it's hard. It's 3-dimensional, right? You could easily make the mistake as you did and draw the triangle in the wrong plane because it's a 3-dimensional plane. Or when I'm sitting here drawing circles and this is supposed to represent a three-dimensional, where's my sphere? You know, I'm trying to say, look at the surface area of this sphere, and I'm drawing this on the paper, and it's like, well, wait, what, and people constantly ask me, why did you use 4 pi r squared and not pi r squared? Well, if you're doing pi r squared, you're thinking 2 dimensions. And then, of course, once you do that, you're talking about the wrong surface anyways. You're talking about the surface of a circle and not this. So I think a big factor is that it's so heavily three-dimensional. Now, in 121, we had our moments of 3 dimensions. When we did a lot of the rotation stuff, and especially something going around a curve, or I know a good one, when you had a car going around a banked incline. You had to have the incline, and then the car banked in a 3-dimension. So if you didn't see this in 3 dimensions, you didn't really understand what direction was the acceleration. So the banked curve is, I think, in the same category as some of these problems where you got to think 3 dimensions for this to make any sense. And we are pre-exposed to more 2-dimensional thinking than 3-dimensional thinking, because we draw things and frankly, they're just easier. We got, so that's an elevation up. And I think the other elevation up is, unlike 121, or maybe I should say 121, we deal with things that are a little more exposed in our just physical world, even if we're not scientists. Motion, all these things that are moving. You've been watching motion since the day you've been born. You learned to ride a bike, at age 3, 4, or 5, and you get a little bit of idea of emotion. So, to talk about position and velocities and accelerations and forces, these are, not really that new to you in 121. But magnetic fields or electric fields, many people have absolutely no pre-exposure to electric fields. Hopefully you got a little bit of it in another science class. But unless you had a hobby of working with electronics or something, you probably don't even have that background like you had in 121 to kind of get a gut feeling for what these should be like. So that's my take on it. Those are the 2 big things. The fact that we're working in a physical world that's not visible with our eyes and common to us like motion is, and we're dealing in a 3-dimensional world. And then it's also, let's not forget, heavily mathematics. I mean, everything I've been doing today, I've been doing all these integrals, and I've even done integrals that have, dot products and vectors. Just the math levels hard. So anyways, all 3 of those together, I think just makes this, which is why I would say, you said you didn't agree, and that's fine. Everybody has their own exposure, but that's why I think 26 comes out to be a little easier than what we're doing now in 24, because we don't really have all this vector stuff, and there's really not any problems involving calculus. Now, that's not to say we didn't use the calculus to get there, because when you do most of the problems that say do capacitance, you have to jump back to chapters 25 and 24 to do them. So you are using them, but I guess I don't give 26 the credit. I'm saying you're using something you already learned in those ones for 26.
Well, I think as far as like getting the points on the exam, it might be the easiest, because what you're saying, like capacitance in parallel, add them up, capacitance in a series, do the one, like I could do that, but like I still have no idea why capacitors connected in series have the same charge, while capacitors connected in parallel have the same voltage. And I read the stack exchange posts and I can tell they're explaining it, but I'm not getting, or they'll go like a non-physical route, right? Like 80% of the time they like show me all the theorems, and I'm like, I'm sure, like I totally trust
Yeah.
that all these equations like shake out to give the result. You're just like, but physically, when with these electrons, you know, it doesn't sit right. And I know that's on my end, but you gotta tell me physically what's going on. And so
Well,
that's the,
do you want me to try to answer that? Why capacitors in series?
sure. Yeah.
All right. So I will try to point out why series they have the same charge. And if I'm successful there, I'll try parallel. They have the same voltage. So series, and I think you got this last time we were talking, that a series capacitor means this. You have two metal plates, and each of those metal plates has a wire coming off. We call those electrodes. And series means that you connect one of the plates. So let me call this capacitor 1. So I'm going to call this capacitor 1, and this first one, I'll call it plate A and plate B. And so you connect plate B of capacitor 1 to a plate on capacitor 2. Let me again call that A and B. All right, so that's series. And the whole reason it's called series is this, that if I were to hook this to the negative terminal of a battery, okay, and not that this part is needed for what I'm after, but you touched on it last time, that the electron that leaves this post really doesn't go all the way through to plate A. It moves into the wire, which pushes another one, which pushes another one, which pushes another one, and it each step pushes the one adjacent to it. But what definitely ends up happening is one electron ends up getting onto plate A, and its original cause is from the electron that came out of the redox reaction of the battery. Okay, so that's a side note, and I think you kind of touched on that last time. But watch what happens next. This electron that's on plate A stays there. Okay. It does not move over to plate B. However, plate B does feel the effect of that electron because there is an electric field between. And what that will do is take the one of the electrons that was on plate B and push it into the wire, which pushes the next, which pushes the next, which pushes the next, which pushes the next, which pushes the next. And then on plate A of the second capacitor, we get that electron on here. And let me point out that on plate B of capacitor 1, we are now lacking one electron.
Okay, so I can see like by extension that you could have like 100 of these, and everyone's just kind of like moves over one.
But notice two things. One you're asking about. One, notice then that the magnitude of the charge on plates A and B are going to be the same. One is going to be positive and one is going to be negative. Then notice that the charge on plate A on capacitor number 2 is coming from plate B of capacitor number 1. So A will have the same amount of charge that left B, which is the same as A of number 1. So that means these two capacitors are going to end up with the same charge on them. There's no other way to get it. It comes from the charge on number 2 comes from number 1. So 2 is forced to have always the same charge as number 1. It has no place else to get it.
Okay. Yeah, it's conservation of charge, right?
Yes. And so the short answer is conservation of charge. Because if these electrons have to go somewhere, they don't just magically disappear, or they aren't just created. And so whatever is on A, plate A of number 2 came from plate B of number 1.
Okay, awesome. That sits with me. That's
Okay.
good.
Yeah. All right. Now, if you're good with that, the other one's a little bit harder. But I'll kind of draw the same picture here. This time I will do plate A, plate B. Ooh. Oh, I think I got a lot of ink in here. Let me put some pressure on it. Maybe it seemed like my pen was drying out. I was like, I think that was that old of a pen. Okay. All right. So let me call this capacitor 1. And let me draw here capacitor 2 in plate A, plate B. And of course, they're hooked up or wired a little different. So the behavior is different. That's why you're discovering we make such a big deal about, okay, is it series or is it parallel? In fact, sadly, sometimes we make such a big deal out of it, we forget that there's also neither. So you'll hear me say that a lot, that be careful. We keep talking about these things hooked in series and parallel, and we almost imply like that's our only option. And if we only have 2, that is our only option. But if you have a bunch, well, so hold off on that.
You could have are you saying you could have like a combination of series and parallel? I mean, there's not like some third.
No, I'm saying you can have situations where it's wired in such a way that you won't get the same charge and you also won't get the same voltage.
Okay, all right.
But let's start with building up to that.
Okay.
All right. I think we do a lot of that in chapter 28. Okay, so got a little ways to go. All right, and then let me put the battery down here. And so here's the negative terminal, positive, drawing what looks like a car battery to me, a little lead acid car battery here. So maybe I'll just put 12 volts. 12 volts. Okay, but parallel means this. And as the name implies, maybe I'll go back to the name in series. You can see the name in series because it's got to go in here to 1 before it gets ejected out. Now, I know it's not the same electron, but it goes out and goes to number 2. So 1 has to go to 2, 2 would have to go to 3. It would be like taking, our physics class. You have to go from 121 to 122. It's a series. You can't go to 122 till you take 121. You got to do it first. Okay. Now, parallel, and the reason it's called parallel, kind of like parallel lanes on a freeway. If an electron comes out of this battery and bumps 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 and bumps, right here at this node, a fancy electronic word for a junction. So at this node, this electron has an option. Which way do I go? Now, I would say the first one doesn't really care. There is no reason not to go on to number 2 versus number 1. In fact, number 2 is a little closer. So I might say, well, let's go to number 2, although I'm not sure the electron would know it's closer at that point. But for the sake of discussion, let me just say it goes on number 2 first until it bumps and bumps and bumps. So you get a negative. And like we said before, that one electron doesn't leave plate A, but it does create a field which chases an electron off of B, which bumps and bumps and, finishes the connection. So that's what would happen with the first electron. Now, here's why we call it parallel, because then the second chemical reaction and the second electron bumps, 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 and it gets to this node and it can feel an electrical push from that other negative. And because of that, it'll say, let's go this direction. Because it's going to go whichever is pushing back the least. And so it gets pushed in this direction. So the second electron goes over to here. And so that electron goes on plate A of capacitor 1, chases one off. Okay. But do you see how these two electrons went different paths? They're parallel. So hence the name parallel. Okay, now here's where it gets fun. Look at number 3. Number 3 comes on up, gets to this node, and it's going to go the least push. Now, a wrong and naive thought would be, well, they each have one. They push the same. No, because these plates maybe aren't the same size. The capacitors perhaps aren't the same size. Let me show you by math. Capacitance is charge over volt. These two right now have the same charge on them, one electron. If they don't have the same capacitance, they will not have the same voltage. One electron does not create the same amount of voltage. In fact, you can see by moving the V to this side of the equation, at this point, if they have the same Q, the one with the bigger capacitance, well, let me make number 1 like a big plate. So it's got a bigger capacitance. There's actually less voltage here than here. And that means there's less of a push backwards. So when the third one gets here, it goes, well, there's a big push here. Let me go here. And so the second one would go on the capacitor with the bigger capacitance. Okay, now here's what gets even still more interesting. Let's look at the fourth electron. The fourth electron comes down here, gets to this node. Which way will it go? Now again, if you're a little naive, you might say, well, there's 2 electrons over here and only 1 here, so it's going to be less push this way. No, not necessarily. Because even though capacitor 1 has twice the charge, if its capacitance is actually more than twice that of number 2, the voltage here on number 1 is still less. And there's less of a push. Or put another way, these guys are so spread out that this third electron could actually go on this capacitor and be further spread out from its neighbors than if it went over here.
It's like pressure equalizing, like it's.
Yes, and here's a good example. If I had a container that was going to fill up with water and a bigger container that I want to fill up with water, and I have this giant reservoir over here, water, and I put a hose to fill them up from the bottom, the water flows in and it doesn't fill the first one all the way up to the top before it starts filling up the second one.
I like this analogy. Yeah, okay.
It keeps the pressure the same. It doesn't
keep the volume. The volume is different, the amount of charge. Yeah.
So the amount of charge is different, but the pressure is always the same. And that's what happens with capacitors. They will always be filling up, so their voltage is the same. And so just like these two containers would always fill up so that they're the same level, and eventually they would get to the same level as the reservoir, and their pressure would be pushing back on the reservoir. The reservoir wouldn't add any more water. This battery would do the same thing. So this capacitor would build up, and first it would be 1 volt, but so would this. It would be 2 volts, and so would this. It would be 3 volts, and so would this. And eventually it would get to 12 volts, and so would this. And then it would stop. That would be full capacity. And so both of them would end up getting to the same pressure, up to the same voltage. And if they're at the same voltage, but have different capacitance, they end up having different charges on them.
Okay. Yeah, that's really good.
So
I feel really secure in that one. I feel secure in the first one. You mind if I'm going to snip this real quick so I can, write it down and make some more long-term notes.
so
My final question is, why isn't the voltage the same in the series case? I mean, I know the capacitances of the two plates could be different. Well, okay, hang on, maybe I got it. The capacitances of the two plates can be whatever we want, and the charge is constrained to be the same.
Mhm.
So if I vary the capacitance, the voltage has to vary because it's the only other variable.
Yeah.
Okay, cool. I got it.
So, and I like the word you use, constraint. So when they're in series, the constraint is they have to have the same charge. When they're in parallel, the constraint is they have to have the same voltage.
Okay, this all really helps a lot.
And then they still relate by this equation, but they have different constraints.
Okay, cool. That answers it for me.
Cool. All right, glad I could do that one. Hey, I think Brendan wanted me to jump back to 31 here. So let's, I'm going to jump over to 31. And I'm going to write down our time factor. So chapter, what is this? 24, number 31, and it is 406 right now. Okay, good. And chapter 24, number 31. Let me figure out where's 31. All right, so 31 says this: a uniformly charged straight filament that is 7 meters in length. Now I'm going to pause there because the last one I did was number 39, or the last one from this chapter in this class was number 39. And we worked out, and I don't know if this is going to come into play, but I might take advantage of it, that the electric field from a charged cylinder was radially outward in a cylindrical direction and was equal to this equation where lambda is the charge. And that's only true if it was really long. And instead of going through Gauss's law again, I'm going to take this 7 meters as them telling me I have a really long enough to justify that if I apply Gauss's law, I will get that. So let me see what they're asking, because if they're asking me to prove that, I'll do it. But if they're asking me to do something else, I might just kind of start here. Okay. So anyways, a uniform charge straight filament, 7 meters in length, has a total positive charge of 2 microcoulombs. An uncharged cardboard cylinder of 2 centimeters in length. Now this is a good one. 2 centimeters in length and 10 centimeters in radius, surrounds the filament at its center, with the filament as the axis. Now, notice they said the cylinder is only 2 centimeters. 2 centimeters is incredibly small compared to 7 meters. And that's the key here. So I'm going to go ahead and in my doodle page here, say, all right, this is this really long wire, 7 meters. And they're asking something about a cardboard piece that has a radius of 10 centimeters, but its length L is only 2 centimeters. So I think I can go ahead and safely argue that if I put this on here, the field is given by this equation, which was derived with Gauss's law back in problem 39 we did about 45 minutes ago. And that one here was done by a symmetry argument that argued that the wire had to be really, really long. And I think we have that. So that is my justification for using this equation. See, and I think that's why it says here in the problem, it says using reasonable approximations. Okay, so like the wire is really long. Find A, the electric field on the surface. Okay, so they are asking us to do this, so I'll do this again. And then the total electric flux through the cylinder. All right, well, let me call this page 1, but let me jump back over here and say, all right, let's actually do this argument. So the first thing to do for Gauss's law, so this is A, is to do this step. Okay, that's the dot product. And maybe I'll go back to my drawing of 39. Here it is. And I was drawing all these lines of symmetry. This is a top view and kind of a 3-dimensional side view and kind of a side view in 2 dimensions here. But this was our argument that the electric field had to be radially outward. It was also our argument that the electric field had to be constant on the Gaussian surface. That's why we did this step here that said, hey, the angle would be 0 and the electric field would be constant. So I'm gonna do that here. I'm gonna pull out the electric field. I'm going to put in cosine of 0 degrees, which is 1. And then I'm going to finish this integral. And not so much by doing the integral itself, but by doing geometry. And maybe I'll grab the page 1 picture that I have. If you kind of just wrap this cylinder here, and you say, okay, what is the area of this? You can unfold it and say, well, it would be length times width. Okay. But if I held it this way, if I call this the length of it, that's the circumference, 2 pi r. And then this would be the L. Maybe I should call this the length. So this is the length. And so this would be the width. And the width would be the circumference. So when it comes to the area here, its width is the circumference, 2 pi r, times its length. That is the area of this little piece of paper. And then the charge inside, okay, would be this Q inside divided by epsilon naught, which means then the electric field would be the charge inside over 2 pi epsilon naught over R over L. And this right here is the charge per length. This is the lambda. And maybe for this problem, we don't need to write it in terms of lambda because they give us charge and length. So I'm going to need these separate. But I just wanted to point out that it does match what I had said. And when I started 31 here, that it's the same thing we got back in 39, which was derived during the lecture and the example. So I'm going to take that and replace lambda with Q over L. Okay. So this, I think we can actually get a number here in 31. It says find the electric field on the surface of the cylinder. All right. So putting in our numbers, the charge per unit length. So the charge is 2 times 10 to the minus 6 coulombs. That is over a distance of 7 meters. So there's the Q and the L. Here's the 2 pi, and I'll just write it as epsilon naught. I'll put that into my calculator. It's 8.85 times 10 to the minus 12. And then the R would be, well, how far away? And they say, find the electric field on the surface of the cylinder. So let me go back. The cylinder, I believe, had a radius of 10 centimeters. I didn't put it in the drawing here, but I'll do that now. 10 centimeters. Okay. So this right here would be 0.10 meters. And the units for epsilon naught are in the bottom, Newton meters squared and coulombs squared. And then that's, of course, very helpful because this coulomb upstairs would cancel with one of them from the epsilon naught. The meters squared and the epsilon naught would cancel with those 2 meters. And you would be left with a coulomb downstairs. And then that Newton here, which is in the bottom of the denominator, would flip when you worked with your compound fractions. You flip and multiply, so that'd be newtons per coulomb. So perfect units for electric field, newtons per coulomb. So if I grab my calculator now, and so on the top, I have 2 times 10 to the minus 6. I'm going to divide that by a 2. I'll divide that by a pi. I'll divide that by epsilon naught, which is 8.85 times 10 to the minus 12. I'll divide that by 0.1. And I'll divide that by 7. And so that would be 51,382, well, depending on significant figures, newtons per coulomb. So there's A. Now the flux might be the easiest one to do here. The flux then is this integral of E dot dA. And I'm going to point out that we essentially did that, right? There it is right there, E dot dA. Now, since we've already figured out what E is from A, we could put that in and go 5,1,382. And then we can put in the 2 pi. We could put in the R as 0.1. And we can put in the L, for the cardboard. We need to be careful here. The flux to the cardboard, right? What is the total flux to the cylinder? Yeah. So the length is only 2 centimeters. So that might be the easiest way, but there's another easy way. So I don't know which would be easier, because the other side of this equation is just the charge enclosed over epsilon naught. And the charge enclosed would be the charge density times the length. And maybe this is a few extra steps because the charge density is that, what was the charge again? 2 times 10 to the minus 6 over 7 meters. That's the charge density of the filament. Now, the length of the cardboard, because we want to know the charge enclosed by the cardboard. So this is the charge density inside the cardboard, which is the same as the whole filament. But the length of it is actually only 0.02. And then we can divide it by epsilon, 8.85 times 10 to the minus 12. So because of Gauss's law, we can get the flux either way, what I call a direct calculation of the flux, where we did electric field and area, or an indirect, where we don't actually calculate the left-hand side, the flux, but we calculate the right-hand side, knowing that it's equal. So let's just see if we get the same thing on both sides. So let me do this left-hand side. I've already got the 51,382. So if I go times pi times 2, so there's 2 pi, times 0.1 times 0.02, I get 646. Now, we want to be careful with our units. This is newtons per coulomb for the electric field, and then this would be square meters. So we don't really have a name for that flux, but that would be the units for it. And hopefully it's the same thing over here. So let me do charge density, 2 microcoulombs divided by 7 meters. So there's the charge density times the length of 0.02. And then if I divide that by epsilon naught, 8.85 times 10 to the minus 12, again, I get 646 for the number. And I guess watching my units here, epsilon naught has units of Newton meters squared in the bottom and coulomb squared in the top. This is charge density, so it's coulombs per meter, and then this is a length in meters. So those meters would cancel off. One of the coulombs would cancel off. You would flip it and get Newton meters squared per coulomb. I think I made a mistake on this side. This is, oh yeah, the meter squared should have been up here. That would be newtons per coulomb, and then that would be meters squared. Yeah, so the units match. Sorry about that. That's the units for the flux, if you want the units. But the point is they match, and the point is we have different options. All right. Well, I think we'll call that good here for the day, and I will hopefully hear from you guys as you kind of work through, and I will send these videos out. Take care.